Hey guys, so we are going to continue. Um, some part of this won't be recorded because I lost my stylus, so I need to write on the board. Sorry. Okay, so the last part of today, we are just gonna look. We're gonna start looking at some of these models, like the pre-trained CNN models, basically. Just kind of get some idea of how they are. And you saw actually in the art style transfer an example of how to grab a VGG, right? And so that's one of the models. And that's kind of what I'm going to do too. So we're going to go over in PyTorch, pure PyTorch, how to grab a ResNet and do something with it. Okay, that's kind of the last idea. But I'll start basically. So you guys, what do you guys know about these models? CNNs, right? That's kind of where you left off basically in 520. You built a CNN of how many layers? 5, 6 layers. And that was a lot of work, right? Building that, getting all that to work. So you're really at that point replicating the ideas that they did in 2012. So as I said, unfortunately, I have to write them. So 2012, okay, what happened there is the big event, the ImageNet challenge, basically, right? And so they used ImageNet, which is like 1,000,000 images, 1,000 classes, and they competed to see who would build the best classifier, best model for classification. So the winners of that were who? You guys know who it was? The winners in 2012? It was a neural network called AlexNet. We'll start there, kind of to think about, where this begins. 2012 is the event that changed really everything about, that made neural networks known to everyone before that. So a lot of the entries to that 2012 competition were not even neural networks. It might have been like other things, support vector machines, something like that. But then AlexNet came in. AlexNet had a accuracy that was 15% higher than everyone else. All right, so 15% higher than everyone else. The name is Alex because of Alek Krashinsky, I think it is, and Ilya Sutsketer, who were the two guys who built that AlexNet. They were students of Geoffrey Hinton at the University of Toronto, right? So they're big guys. AlexNet, I don't know what he's doing. Ilya Sutsketer is like the brains behind OpenAI today. So think about that one person, Ilya Sutsketer, first one to win in 2012 with AlexNet, and now it's literally like the engine. Sam Altman is a great CEO, but the intellectual person is Ilya Sutsketer at OpenAI. All right, so anyway, so that's AlexNet. AlexNet, actually, I have the architecture here, so I'll talk a little bit about that. And then other models are ResNet, something called Inception, and VGGs, right? So we can look at examples of that. Basically, what are they? CNNs, right? But very deep CNNs. And they are CNNs that are pre-trained, and you guys can use them basically by downloading the weights. Does that make sense? So that's what it is. So I'll mention some of these. So we've got AlexNet, then we've got ResNet. Anyone know what ResNet stands for? Residual, right? So but do you know what residual means here? It's important, right?
I know of that. No, and my profession to be very much.
Okay. But yeah, so we'll go over that. We actually use that in transformers already, right? So if you remember in the transformer architecture, we did those residuals. So I talked a little bit about that. Then we have inception models. Inception. And then we have VGGs, basically, which is another type of an architecture. So all of these are basically things that people have done to try to improve the models. What they have in common is that they are CNNs. They're very deep. You're going to want them to be pre-trained, and they use this idea of residuals, basically. So that's the other concept. So we already saw an example with the art style transfer of how to get a model from just torch itself, which is basically to do something like from Torchvision or Torchvision models. That could be dot models, for instance. And then, or we can say as models, or we can just do import model. Import models. And then the nice thing about this is that if you try to do something like dir models, then you can see everything that's available in there, and you can, choose those elements for your GAN, your CGAN, etc., for your mini project. Okay, so that's the idea. So just to give you an example, AlexNet, as I said, won in 2012. It was the state of the art at that point. And AlexNet was trying to predict 10 classes, but the architecture was not very deep. So I'll just kind of draw it here. So you had like an input image, and then you had several convolutions, like 1, 2, 3, 4 maybe, and then 2 normal feed-forward layers, and the final 1,000 class layer. You guys see that? So this was the original AlexNet. Some convolutions, followed by feed forward layers, and the last output layer. And this would be, of course, the input, which is the image, which I think was 96 by 96, for whatever reason. Okay, so that's the example there, and you're basically trying to predict. I think these feed forward layers were 4,096. And you were trying to predict a vector of size 1,000. I actually think some of you last semester in 520 built architectures kind of this deep, right? So maybe 8 CNN layers at most and a few feed-forward layers and so on. Does that make sense, guys? And then this was trained on the ImageNet data set, which was somewhere like 1.4 million images. Back then, that was a lot, okay? All right, so why do I tell you this architecture about AlexNet? Because I want to do the contrast to ResNet, right? So ResNet, then, for example, are way deeper, right? So you can choose your ResNets. You say something like, I'm going to use a ResNet, what is it, 18, right? Or a ResNet. You can have a ResNet 101. And what does that imply? It implies that it's got 101 layers, basically. So this, you could say, has 4 convolutional layers, and 2. A ResNet would have 101. It's very deep. Do you see that? Very deep. So you can say here, 100 has 101 layers. So now, actually, the jump from AlexNet to ResNet had a bit of a difficulty. There was a bit of a problem in making this jump. So what is the name of, so let's say, obviously somebody said, let's say you're Meta or something, you look at AlexNet, they made it deeper, so many layers and so on, they have computational power. Let's just try 100 layers. What do you think happened when they did that? Do you think the models immediately worked? Actually, they didn't. Why? Do you know why they didn't work? What was the problem? What's the problem with very deep neural networks? Anyone know? It actually has a name. That problem is called the vanishing gradients problem. Maybe I've mentioned that, or maybe you guys have read about it somewhere. But so someone was going to say it. So the vanishing gradients problem was like a serious thing. Okay, so you have AlexNet here beats everyone. So definitely this is established. It's not even deep. I think, David, your network was probably deeper than this last year, right? Mm-hmm. And you did it from scratch. But they started trying 18, 101. They expected the neural network to learn, and it actually wasn't learning. And it was because this idea of the vanishing gradients. So what happens is, if you think about it, I'm just going to say like this is the input, and then this is the output, right? And in between, I'm so many layers that I'm just going to do something like this, right? Dot, dot, dot. So what actually happens? The vanishing gradients actually can be explained very simply with this example. And I think I've probably done this. What is that? 0.25, right? What is that? 0.125? What's that one? A small number, right? You guys get the idea, right? It's getting annoying, but let's say 0.0625. I don't know. I'm making it up. What's happening is every time you're multiplying things like weights. What are weights? Weights are usually very small numbers, right? 0.5 is a high weight actually. So you're doing matrix multiplications constantly, right? So where does this happen actually? So you go that way, you predict, right? And the prediction is compared to the real, and then that information is what? Back propagated, right? Back propagated. And as you're doing the operations in the back propagation, you're performing these matrix multiplications. At some point here, values are zero. What's the point of all weights being zero? Do you see that? And so the models just fail. Do you see that? And so that was so hopefully that makes sense, right? So that's called the vanishing gradients problem. And so that needed to be fixed. And that was fixed by something called the residual. And it's something you've already seen in this class because the transformer had residuals. And I remember pointing that out. Okay, so the idea is that, I'm going to erase this. So it's really important, right? Without that fixing of the residuals, we would not have, the neural, ChatGPT or anything like that. It wouldn't be possible because of that. Actually, so what you do usually is you do a whole bunch of operations, right? In some neural network thing, right? That happens, but you get to this processing. But just before you move to the next step, you do the and it's like that, where this is the NN, very deep or whatever. But just before you move on to the next layer, instead of sending res, what do you send? You actually send res plus x. So you see that original data gets sent again. So the original data comes in, goes through whatever all of this is, that produces a value. But that value is not sent directly. You do this plus x. And that's, a simple example that you saw pretty much in the transformers code. And that's the idea of residuals. And that then allows, imagine when this was fixed, now you could have, CNNs such as ResNet of 101 layers, and they were learning. Does that make sense, guys? Any questions? So yeah, so that's a big jump, right? So from AlexNet to ResNets. And then from there, the ResNets get improved, get trained on lots of images, etc. And then you have great weights, basically. Okay. All right. So in PyTorch, you actually have two types of ResNets that you can get. You can get just the architecture, like the 101 layers with everything that you need in there, but without the weights. So then the idea is that you can pre-train that ResNet with your own data. That's one thing, right? One approach that you can get. The other approach, of course, is to actually get the same architecture, but with the weights themselves. And you can use that. That's it. So that's the idea. So that's one of the examples that we're going to explore today in the rest of the class. But I wanted to point that out. So the way that you would be able to implement that would be something like this. So let's say I create a ResNet and I would invoke models, just like we did in the art style transfer example that we saw previously, where I brought in the BGG. And now I do ResNet 101. And then here, you want to say pre-trained equal true. So that you can bring in the weights, and then you can add, you can do this part yourself. So the idea now is you have what? You have an image. It goes into a ResNet. Let's say it's like a big thing like this, ResNet. What is it effectively? What is a ResNet? If, you know, the ResNet is not really predicting classes, right? It's not really predicting classes. Instead, what's it doing? It's just taking this image and processing it. So the way that you can think about this is that this is just a whole bunch of layers of filters, but it's filters that have already been pre-trained, so they're very effective. So essentially what you get out of here, if you will, is a hypercube of the original image, but every layer is like a filtered version of the original image. And that's really handy, right? Because it's me like saying, let's say I take this image, right? And one of the algorithms, for whatever reason, is that I need to, it finds caps. So it's going to put a 1 right there and everything else is zeros. And that's one layer. Do you see that? And then another might be glasses. So then 1, 1, 1, 1, 1, 1, zeros. Do you see that? 0. So that's the same image, but filtered for glass detection. Now, did a human have to create this filter of glass detection? No. Actually, it was the CNN during the pre-training that discovered that filter. Why? Because it found that, you know, given an image, if I find where the glasses are, when I have to go predict intellectual people or something, right? You know, that helps. Does that make sense? So that's basically the idea. Remember that CNNs like this, no human created the filters, the convolutions. Instead, those convolutions, the filters, are learned. But because it's very deep and it looked at a lot of data, it's got really good filters, which translates to really good weights. Okay? So what you get is here is the representation of that. And then after this, what you can do is you can add your own. You can basically, what do you have to do now here? Probably flatten. So you need to flatten that into something corresponding to this one, right? So you don't want to lose data. So you're going to need to flatten to something that corresponds to that. And then after that, you add however many feed forward layers, just the normal nn.linear. So these are nn.linear with possibly with ReLU activations or something like that. And then now you will have your problem. Let's say 5. So this is the output and the classes. Oops. So the classes. You guys see that? So those are the classes basically. So what do you have to do when you train your model? You want to do what? What is this called? You know, you don't want to update those weights, right? So what is that called? It's called freezing. You're going to freeze the weights of those layers, and you're going to leave these not frozen. So then now, when you give it an image, none of this is going to be updated. Instead, the image goes, and it becomes this. But once it comes out here, then it goes into this neural network part to predict a class. That class is compared to the real, back propagated, and you only update these weights without updating the other ones. Basically, okay? So that's what you can do. So if you want to consider this for your CGAN, you know, as part of the architecture, go ahead. That's kind of what I'm doing here. I'm just showing you this idea, okay? And I do have some PyTorch code where I'll show you how you can freeze and unfreeze the layers. So yeah. Okay. All right. So hopefully that made sense. So anyway, so today we're just talking about grabbing these models from the hub, basically, such as ResNets, etc. And I talked about residuals, so that's done. And then inception and VGGs, you've seen an example of that one, but we might cover those next lecture. Okay, so for instance, if you wanted to get AlexNet, you would use something like this. We'll call it AlexNet. And then for models, dot AlexNet. All right. Yeah, so unfortunately, I lost my my stylus. I have to buy a new one. But anyway, that's kind of a little bit of the background that I wanted to give you just to kind of get a feel for how it works. And then we're just going to now try to code it up in PyTorch. See a very simple example of freezing the weights, of grabbing one of these pre-trained models, etc. Okay? All right, so let's go ahead and I'm going to probably need to create a new script. Yeah, right. So I'm going to create a new one. Rename. And let's just say a simple example, ResNet maybe. ResNet. From Torch. Freeze layers. Okay. All right. So I'm going to hit rename here. Okay. So we're going to need some libraries such as Torchvision, etc. So let's do from Torchvision import transforms. Okay, so a lot of this sometimes was going to be transforming the image. So we're going to need to resize it, center crop it, convert it to tensor, normalize it, all that. We're going to need to invoke a ResNet model. And just do inference with it for now. Okay. So I'm going to use this as a basis. I'm just going to grab. This is from the art style transfer example. So I'm just going to copy some of the libraries. All right, so I'm going to use torch NN, functional, pill image, and then I have Torchvision. Yeah, so it's the same and models basically. Okay. All right, so now I'm going to bring in ResNet. Hold on. There it is. So let's try just looking at so this is basically where I'm trying to bring in all the models, right? So I'm going to just do models, run. Okay, Torchvision models. Now I'm going to try dir models, basically. And there they are. All of them that you can play with. So this is really what you can use. So AlexNet is right there. First one, AlexNet weights. So this is what I was saying. So some of them have the weights, some of them don't have the weights. I don't know all these, but some of the, there's GoogleNet. There's Inception, this is Inception version 3 is supposed to be a very powerful one. So it's one that you might want to play with. Vision Transformer, maybe. So that might be a new one. So yeah, actually, they might have some transformer-based ones in here. MobileNet, right? So for those of you doing like mobile apps, so these might have a smaller footprint. ResNet, so you can see, these 101, ResNet 50, different dimensions for the images, ResNet 101, 18, 50. And then there's VGGs. These are also a big popular one. VGGs. I think when they've compared VGGs to ResNets have been the better model. So different sizes there. VIT, I want to say this is a vision transformer. Yeah, there it is, vision transformer. I think the last time I looked at this, I didn't think of vision transformers, and now they're there, right? So something that I haven't played with, but it's interesting. All right, and then basically these are all the different ones. ResNet, as I said, 101. This is probably one that we're going to play with. BGG and so on. Okay, so we've seen the models that are available from Torchvision. So we don't necessarily have to use FastAI or some other framework to get pre-trained models. We can just use something such as this. Okay, so now the next step is probably to bring in one of these models with weights, okay, and then try to do something with it. So let's try AlexNet. So I'm going to say AlexNet equal models dot AlexNet. I think that's how it was spelled. Okay, no errors. Let's take a look. AlexNet. And there you go. What are you seeing here? You're seeing actually the entire architecture of the AlexNet. What do you guys think? So it uses NN sequential, right? Which you guys know how to use. Then it's got a convolution with a ReLU and a max pool, then another convolution with a ReLU and a max pool, then another convolution with a ReLU and no max pool there. Then another convolution and a fifth convolution. So actually it seems to have 5 convolutions, right? For the processing there. And then it's got the linear functions over here. So it's got this adaptive pooling. And then you can see here linear. The 2 linears 496, but we're at the end. And then the output features here are 1000. Do you guys see that? So that is, if you're interested in this is actually, I would say AI history, right? So if you want to be an AI archaeologist, go there to AlexNet. That's changed everything. Okay, so anyway, that's the algorithm. Okay, so let's keep going. Just play with this a little bit more. And hopefully you guys will incorporate this into your mini project. That's kind of my goal. So we can repeat the same process for the other ones. Oh yeah, ResNet. So I'm going to say ResNet. So it's going to be models dot ResNet 101, and we should say pre-trained equal true. Okay, so to get a pre-trained ResNet, oh, you don't like it? Pre-trained. Huh?
I think you spelled trained wrong.
Did I? Oh, sorry. Thank you. Sorry. Yeah. Okay. So yeah, just an example of how to bring in our ResNet. So again, keep in mind that's a ResNet 101, very powerful model. The model will take images of a specific size and then it'll give you an output, right? So that's kind of the idea. Okay, so we've done that. So now we probably want to take the same approach. We want to do ResNet like that. Hit run. Okay. That gives us the exact architecture of this ResNet algorithm. So as you can see, a bit longer, right? All right, or deeper, rather. This is probably one of the deepest neural networks you'll see, right? Because I don't think transformers are this deep technically, right? They have 6 blocks and there's a lot going on. I don't know, I guess, how that translates, but this is basically your ResNet architecture. So it's got convolutions, right? And many operations. So that's another thing, like this uses everything that is useful. Batch normalization, ReLU activation functions. So everything that you've probably tried in your own from scratch CNNs, this will have it in there. A lot of great parameters. So it's very difficult for you to build your own from scratch that will be as good as this one, basically. Okay, so take a look all the way to the output. What do you guys see? So the output is 1,000. So what does that tell you? Is this model was trained pretty much on the same data set as AlexNet. So if you ever wanted to convince yourself, benchmark AlexNet against ResNet, right, on the same task, and you should be able to get the performance. Does that make sense, guys? So you can take a look. So what this means to me is that actually, so I thought this was going to give me something like this, right? But this will actually give me a class. So basically, it can do inference. So if I know the dictionary of the 1,000 numbers, I give it an image, it's going to predict, let's say, class 99, and I just have to look up 99 in a dictionary, and I'll know that's a dog or something like that. You see that? So obviously, if you're using, so if now you got to ask yourself, if you want to use ResNet with your own classifier data and fine tuning, you'll have to do what? You'll have to probably strip at least this layer, right? You have to take that out and put in your own layers and your own classes that you're trying to predict. You guys see that? It's a pretty important concept. That's what transformers do for you, right? Transformers make it very easy for you to just change the heads. And that's what those things are called. Remember the head. So this last part, we have to strip it out. Say from here and add our own, basically, so that we can fine tune those. But this model, actually, ResNet 101, goes all the way to that 1,000 class. So we, in theory, should be able to predict. So let's go ahead and do that. Let's try to do some inference with this model. Okay, so we're going to need an image. I don't really, I'll grab one of the images, I guess, that I have here. What do I have? Oh, I'll grab, you know what I'll grab? That ballerina one, because that's a person. Yeah, so where is it? Hmm. Do you guys see it? Oh, there it is. No, that's Ballerina Picasso. Dancing, where is that? Dancing JPEG. Okay, yeah, that's probably it. Okay, thank you. All right, so let's try and load that image. So I'm going to say, I'm going to use pill for this, which you guys are familiar with that, pill image, right? So img equal image dot open, and I'm going to bring in dancing dot jpeg, I think it was. Okay, so let's try it first. Worked. See if we can look at it. img. Okay, there we go. So we've got ballerina or dancing image. So now we're gonna basically try to run this image through the ResNet. That's kind of the goal. So we have our pill image. We can also do something like img dot show. And that really does not work here, right? So, but we've already seen it. Right, so one thing we may need to do is define a function to pre-process the image, because we need it to be not a pill image, but we need it to be what? A torch tensor, resized and everything, right? So we're going to use transforms for that, which I believe it's already imported here. So I'm going to define that function. I'm going to call it pre-process transforms dot compose. And that is open parentheses, close parentheses. Okay, and now I'm going to put in a list basically of items. So I'm going to do square bracket, close square bracket, like that, okay? So I'm defining this construct, and then I should be able to pre-process any image, hopefully. As you can see, I'm trying just a random image in a sense. That image is color, I think it was, yeah. So that's one issue to think about. So I'm going to do from transforms. So compose allows me to put several transforms in there. I think we did this in the beginning of the semester. So I'm going to do transforms dot resize. And this ResNet in particular, we can resize it to 256 first. Okay. Obviously, we may need to improve this. Then we're going to center crop. So I'm going to do transforms dot center crop, and that's going to be 224, right? And then we need to convert it to a tensor, obviously. So I'm going to do transforms dot to tensor. To tensor. We also need to normalize it, but let's just try this for now. I just want to make sure that this will run. Yeah. Okay. So in this case, we define a process function that will scale the input image to 256 by 256 and then crop the image to 224 by 224 and transform it into a tensor. Okay, and this should be a color image. So now we will pass the image through this function. Okay, so let's first run this. Okay, that worked, no errors. Now the image ballerina, that I'm going to say img underscore t pre-process, and the input to it should be img. Okay, so no errors. Good sign. In theory, this should be a tensor now. So imgt dot shape. Okay, and it is a 3 by 224 by 224. Perfect. It's an RGB 224 by 224, and it is in the format that PyTorch likes. Okay, so now we can go ahead and we may need to, oh, we've done this trick before. We need to create a batch, right? Because the things like batches. So how do you do that, guys? It's just a batch of one in this case, right? So I'm going to call it batch t equal. So how do I create a batch? But to create, right, okay, so to create batches, what I mean is we need to add, yeah, I see where you're, but what I mean is, instead of being a tensor 3 by 224 by 224, we need it to be a tensor 1 by 3 by 224 by 224. That's what I mean, the batch, because we would give it batches of 16 and so on. We did this last week, actually, for the CGAN and so on. So do you guys remember how to do that? One of those commands that you should like memorize if you do this regularly, and that's basically our squeeze and unsqueeze. Remember those? Okay, so that's what they're for, right? So, all right, so let's go ahead and try that one. So I'm going to do torch dot unsqueeze. In this case, we want to unsqueeze it. Unsqueeze. And then we're going to say img underscore t comma 0, right? Because it's in the first dimension. And then we're going to print the shape of batch underscore t. So I'm going to do dot shape. So now I'm going to run that one. And as you can see, we have now unsqueezed our image to be 1 by 3 by 224. Okay, so that's done. And now we are sort of ready to run our ResNet, right? So it's like fast AI, right? In a sense. So you don't necessarily have to do all that thing of fast AI in a sense. So hopefully it'll tell us that it's a person. That's kind of where I'm hoping. So the model is ResNet, so we're going to need that one. We know that it's going to predict 1 of 1,000 classes. So it's going to be ResNet. And now I'm going to go ahead and I'm going to change the mode of the model to eval, which basically means that it's not training mode. I'm going to put it in inference mode. Okay, like no torch grad kind of thing. So I'm just going to do dot eval like that, parentheses. So let's, okay, so it just loads the model, but should be good to go. Okay. This one. All right. And yeah, it prints out the architecture. So now let's predict. So I'm going to say let's say pred, right? Prediction. And I'm going to invoke the ResNet ResNet. And of course, I need to give it as input what? Batch T. Batch underscore T, like that. Make sense? All right, so let's try that one. Okay, took a little bit, but it did it. Now, if we print pred, got a lot of data in there, right? So this is probably not meaningful to us. So something more meaningful might be to print shape. Is it as expected? Yeah, it's predicting that last vector of size 1000. Remember, as I said, if you want to use a ResNet with your own classification, you're going to have to remove those last layers and add a new head with your new classes. So the question is now we need to get the class of what we're trying to predict, right? So we need to get that. So it's got 2 dimensions. So I need to so I'm going to do the following. Underscore, and maybe you guys can help me. I'm going to need the 1000 labels in the ImageNet data set. Okay, so I need to know what that number will correspond to. So maybe that's online. So I'm gonna do index, right? And I'm going to use torch.max, which you have used before. Remember, this returns the value and the index, the highest, sorry, I should say the highest value and that corresponding index. So I'm going to do torch max of what? Of pred, comma, on dimension 1, because I want it to be applied on this dimension over here. Make sense? So now let's go ahead and run that. Okay, we've got it. And now comes the moment of truth. 601. So all we need is the dictionary or whatever it is of ImageNet that corresponds numbers to classes, and we will know what it predicted, basically. So I don't know if you guys can Google that. I can Google it myself. I don't have that. It's something called ImageNet underscore classes txt. It's a file. But we can use that index. To obtain the line label. I'm gonna look for it. So really just if I'm gonna look for ImageNet underscore classes.txt. Oh, you found it?
It classifies it as hoop skirt.
About what?
A hoop skirt.
Yeah, that's what I got too.
So the skirt that she is wearing, it's finding the skirt.
A hoop skirt.
Yeah.
What is a hoop skirt? All right.
I imagine a hoop, like a hula hoop, and that's how the skirt looks.
Okay, so like a cone shaped thing, maybe. Oh, okay, yeah. Yeah, right?
That's weirdly specific. That it like found like more than just a person.
Yeah, that's not, I think that's good. So you found the file, right? It's ImageNet. I mean, if you guys have other images, you can try them too. ImageNet underscore classes dot txt. Yeah, so on GitHub, apparently, it's available. 601. What is it? 601. I probably ran out of time. Yeah. All right, but we finished it. So 601, I also, no, I found something that says it's a hatchet.
What?
No, hoop skirt, sorry. No, you're right. Hoop skirt. All right. Yep. Great. All right. So that's basically how to use a pre-trained model. The other thing I want to show you guys is how to freeze and unfreeze the layers, okay, of a neural net. So we're going to do that. I'm going to need to get a new GPU here. Okay, so I'm going to close this one. Jupyter Notebook. Launch. Give it a second.
Is that a 1 TB that you're using 16 terabytes?
Yeah, that's a Civis thing.
Oh, so that's like the interview. Okay.
Yeah, something else. This is taking a while. Try again. All right, so while it's doing that, I guess let's go. So are there any questions with that idea? I know it caught off a little bit, but that was an example. I wanted to kind of do a review of it. But I'm not getting this. So that was an example of bringing in a pre-trained model using just the default PyTorch hub. We talked about ResNet in its background and everything, and then basically we were able to use our pre-trained ResNet for inference, basically, as you saw, right? And so you can play with that. I showed you how to look at all the other models. So I encourage you to play with that and to use it on your final mini project, okay? As you see fit. The other thing I want to show you now is this idea of freezing layers, freezing and unfreezing layers, right? So I have another, that will close with that today. I have another script for that.
Just a reminder, how long do we need to unfreeze something?
Oh, that's right. You need to present, right?
Yeah.
Okay. Yeah, you know what? Let's do that next week. Okay, so that we have enough time for you to do your presentation and anyone else that needs to present. Okay, how about that? Because I don't know, I'm not getting that GPU. Oh, just got it. Anyway, let's do your thing. So, well, you wanted to do it last week also, and I've been delaying you. So let's do that. Thank you. So I'm gonna stop sharing here. Close it. Just